Yeah, so I'd love to learn a little bit more about how FPGAs were being used, right? What context? Why were they the optimal or a good solution for what y'all were doing at GE? Maybe when you initially got introduced to them.
I think so. I mean, some of it I think is the longevity there and the ability to change and morph the design. I would say like we kind of went through a transition, from when I first started, or maybe even before I first started, back in like '06, '07, into now, where like the it was hard to find processors that were like fast enough to do some of the things that we needed to do as well.
Mm.
So if you need like hard real time stuff like data processing or I mean we can talk a little bit briefly about like a CT scanner is basically has an x-ray tube, and the x-ray tube shoots x-rays through the patient who's kind of in the middle of the tube, and it spins around the patient. And apologies to any physicists, but like the really simple version is you basically take pictures at a bunch of different angles around the patient, and then put those all back together into a 3D model of the patient's body. And like the detector can tell how much stuff the x-rays went through given their attenuation and that kind of thing. And so the way that reconstruction is done is by it's a process called filtered back projection. And so when I first joined, or when I was first there as an intern, we were the team was using FPGAs to do filtered back projection because the data rates were so high. And we're talking 850 megabit, or and so like not high in today's world, but high at the
Right.
time. And so you're not like, and we didn't really have, gosh, in 2006, 2005, 2004, like what was your video card? Like a GeForce 2 maybe, or a
Right.
GeForce 3. Like we didn't have this big GPU offload. And so in order to make those to reconstruct those images in a reasonable amount of time, you sort of needed dedicated hardware. And so some people would go off and make ASICs, but like the algorithms change, and that's a big spot where like you want to be able to iterate on your algorithm, and you
Mm.
want to be able to change things, and you may find enhancements, or and so they used filtered FPGAs for filtered back projection. So there was a PCIX board back in the PCIX days that had an FPGA on there, and the computer would catch all the data and then run it through the FPGA to do filtered back projection. The same thing on the acquisition side. So up on the rotating side, you have you need to somehow like tell the system to take all those pictures,
Hmm.
and that becomes a fairly real time thing. And you have an encoder basically that tells you what angle you're at as you spin around the patient, and you need to somehow correlate that to your image snapshots and make sure that your periods are all lined up. And depending on your algorithms, like you want them to be fairly precise, because if you're assuming the angles are perfect, any imperfection in the actual sample of the data ends up turning into like poor images, right? So if
Hmm.
you think you're going every 2 degrees and you're really going every 2.1 degrees, like your image is going to be a little bit messed up when you reconstruct that. And so there's some real-time applications there. And then again, like the data rates you're running, the other thing is the CT scanner spins. And so like very early versions of CT scanners would spin once to like get up to speed, spin around the person once to acquire, and then spin once slowly to stop. And they had a cable that basically like spooled up and unspooled when they did this. And then they'd
Oh.
reverse that process backwards, right? It turns out like that has a lot of problems.
Right.
And so, and then you also have like a lot of spinning things are easy when you don't have a patient in the center, but because you have a patient in the center, there's no like coaxial place to like, put like butt up two optics or anything. So you have to somehow get all of this data from the rotating side to the stationary side. And there's a bunch of like, somewhat proprietary technology that most of the CT scanner systems use these days. And we call that a slip ring, but basically you have to shoot the data across a gap. And in order to get the data across a gap, you need to run a custom protocol. And so, we can talk about 8B10B protocol. So we have, as you're shooting data across what is effectively a capacitor, it's
Hmm.
like an AC coupled link. And so you need to limit the number of ones and zeros that you run in a row, because otherwise you start to bias that capacitor, and like it stops acting
Ah.
like a short at high frequencies, right? So because capacitors at high frequencies are shorts, and so You're looking for like protocols that do some kind of encoding. 8B, 10B basically takes every 8-bit code word that you want to send, converts it into 10 bits, and it has a positive disparity and a negative disparity. And then the algorithm keeps track of whether you have too many ones or too many zeros going, and will pick the opposite code word in order to balance the link out. And so with 8B, 10B, if I remember right, you get like you can have 5 bits of a 1 or 5 bits of a 0 before you're guaranteed to see a transition, but that helps keep your link, DC balanced,
Right.
and at the cost of a 20% efficiency hit. So, right. So every 8 bits I'm meant to send, I'm actually having to send 10 bits. So I'm paying a 20% penalty in order to get this encoding. And so as you look at other systems, like Ethernet, I think uses 6466. So they're paying something like, what is that, 3% of a penalty for their encoding. So it's a lot more efficient, but the number of the run link limit is like 80 bits instead of 5. And so that didn't work for, the physical ring technology. So you had FPGAs up on the station or the rotating side in order to encode that data and shoot it across this link, and FPGAs on the receiving side to decode that data and, split it all back out. And, kind of all kinds of control. I mean, most of the subsystems, I think, had FPGAs, and, they were used for various things. We also did a lot of soft-core processors there. And so, rather than buy a, like 68,000 microcontroller or, buy a microcontroller, we would stick one in the FPGA. And so we had a number of subsystems that would run on soft-core processors. And, they didn't need to be super performant. They're mostly like, you kind of let the FPGA do the real-time stuff, and they just kind of monitor and report and do like setup and cleanup at the end. And, so it's not there's a lot of software there, but it doesn't have to be, you're okay on a 150 megahertz processor, and as long as it can talk Ethernet or, what have you. So.
Right. And so you mentioned the PCIX board. So y'all were not actually designing the boards that the FPGAs are on. You were just integrating them into your system.
So
is that right?
Nope, that was a custom board. And, and at the time, I'm not sure what. Nowadays, you can go out to an integrator and go find like a compute module, right? So you can get a PCIe card with an FPGA on there to do general purpose, compute. I'm not sure what existed back in that time, but that was definitely custom hardware. And so it was like that was a custom design, and then you put that into a PC that was mostly off the shelf, and that would oftentimes those were used. They had a custom heatsink on there and everything. So they're in there doing that. As we progressed, I kind of alluded to this before. Some of that stuff got eaten by GPUs because it's easier to just go buy a commodity GPU and do your back projection on a GPU-based algorithm. You can use OpenCL or what have you, and do that a little more efficiently. So in later generations of the system, you see the FPGAs kind of moving out of the actual like back projection and the image processing flow, and more, but staying and even increasing in the like the data acquisition and the data capture side, right? And so on a later gen system, for example, we had an FPGA that would catch all of the data from the slip ring and then turn that into TCP packets. And so we had our own custom like TCP offload engine there, where we can buy a commodity computer, and the commodity computer can connect with 10 gigabit Ethernet, one or more 10 gigabit Ethernet to this card, open up a TCP stream, and then just catch all of the data basically flying, in the system, and keep track of it and store it to disk and everything. So that got us kind of out of some of our like, can we put our custom stuff inside this other computer? And you get into like warranty challenge, logistics challenges, and all kinds of stuff there.